For example number 2, we are going to use the same information as in example 1, but we will rotate the region about the y-axis, not about the x-axis. So first of all, let's do a picture. So we use the Cartesian plane where let me erase this one. Oh, that's fine. So we got from -1 to 1, and that's a radius of 2. All right, and this is our region of rotation, that section of the arc right here. But in this case, we're not going to do the rotation about the x-axis. Recall what we did last time. That gave rise to a solid that looked like a Parmesan cheese. Remember, we made the analogy. This time we're going to revolve this around about the y-axis instead. We're going to do this instead. And this is going to give us a totally different solid in this case. Well, let me draw this counterpart. And well, of course, the solid generated is going to look like this. Alright, so it's going to look like a cylinder in this case with curvy top and bottom. Alright, so now this is where we are going to set up the problem. Number 1, well, in general, surface area, big S, equals to 2 pi, the integral from a to b of f, or not f of x yet, we don't know whether it is f or. So this is just r of x, which is the radius in this case. R of x, square root of 1 plus f prime, quantity squared, with respect to x. Okay, so let's look at the region of rotation again. You can always think of candy, the lollipop, you know. So the radius, it's always the distance from the axis of rotation to the outermost points in the shape of the candy, for example. And in this case, this happens to be this distance, this horizontal distance x. In this case, it's x units away, as opposed to the previous example when we did the rotation about the x-axis. We had a vertical distance. You know, we have points that were a vertical amount of units from the axis of revolution to the outermost point on the solid. So here, okay, let me replace this with 2 pi integral from a to b of x square root 1 plus f prime squared with respect to x. All right, but in this case the question is x, are we working with functions of x or with functions of y? Well, since in this case we're repeating the exercise exercise 1, we're still keeping functions of x. So in this case, x, it's going to be x because that's a function of x. Things are going to change later when we will express this x as a function of y. All right, but not in this case. So okay, it's time to do the substitution. So 2 pi, the integral from -1 to 1 of x times the square root of, okay, so to avoid wasting a lot of time from last time, so this is what we got from last time. So, well, first of all, the derivative of the given function, we got it to be negative x over the square root of 4 minus x squared, right? Quantity squared. And of course we did a bunch of of algebraic steps to simplify that. I'm just going to skip all those steps. Of course, all the details for that simplification are in example 1. So I'm going to go to this point, to pi, integral from -1 to 1 for x, the square root, well, that was not the square root, that got simplified to 2 over the square root of 4 minus x squared dx. Alright? And while cleaning this up a little bit, well, let me take that 2 outside of the integral to multiply with the 2 pi. And let me have that x on top of the radical in the numerator here. So that's a 4 pi integral from -1 to 1 of x over the square root of 4 minus x squared dx. All right. So, okay, so here's the thing again. You could evaluate this integral this way, that's fine. However, you might want to take advantage of the symmetric property for the region that we have, because instead of integrating from -1 to 1, like having to do a big back substitution, having to evaluate with a lot of negatives that we have here, we can make one of these limits to be a 0, and that's going to simplify a lot of the work, and that's what I'm going to do. So instead of integrating from -1 to 1, I'm going to integrate from 0 to 1. And okay, let me change color here. And multiply by 2. So integrating from 0 to 1 and multiply that by 2, so we can easily get the surface area for the whole region. So that's going to become x over the square root of 4 minus x squared dx, which equals 8 pi and that's a dx. Okay, so here is where we're going to do the u substitution part. All right, so okay, so I'm using the x. U sub. So u equals to 4 minus x squared du equals -2x dx. All right, and in this case, well, let's solve for x dx, which is -1/2 du. But again, since we are using the u substitution here, it would be a good idea to also change the limits of integration, so we don't have to do a back substitution right a lot, and we can just do the fundamental theorem of calculus basically in one shot in terms of u. So for this, I'm going to do u equals to, u of 0 and u of 1. For u of 0, that's a 4 minus 0 squared and 4 minus 1 squared. 4 and 3 respectively. All right. And I know this might look a little bit weird at the beginning, because we will end up with a larger lower limit than upper limit. And that's fine. In the end, you will see how, because of the signs, it's going to make it a lot better. So, or it's going to work better. So that's too small. Okay, that's good. So let me continue here. So this will be equal to, 8 pi times the integral from 4 to 3. And this x dx becomes a -1/2 du and the square root of u in the denominator. All right. So let me take that 1/2 out of the integral. So that's 8 pi times negative 1/2. That's going to become a negative 4 pi. And that's the integral. And that's u to the 1/2. The u from 4 to 3. Of course, we cannot integrate while the u is in the denominator. We need to move it to the numerator with negative exponent. And just use the general power rule to integrate. So add 1 to the exponent, divide by the new exponent, negative 1/2 plus 1/2. That equals to 1/2. Evaluate it from 4 to 3. Well, dividing by 1/2 is the same as multiplying by 2. So that multiplication by 2 is going to go with the negative 4 pi, giving us a negative 8 pi. And then that times, okay, not yet, times the square root of u from 4 to 3. And that equals to negative 8 pi. Square root of 3 minus square root of 4. But what's the square root of 4 in this case? Well, this one is a really nice number as opposed to the square root of 3. So that's square root of 3 minus 2. And that's essentially final answer. However, if you don't like that negative value in front of it, you might want to use it to distribute and reverse the order of these two terms, which is a lot better. That way doesn't make it look like it's a negative number, because of course we are supposed to get positive values for areas, volumes, etc. Right? So 8 pi 2 minus root of 3. Final answer. Let me zoom it out. Questions about this one? Questions about the setup? Questions about the integration? Again?
If you didn't do the inverse thing that you did, where you set the interval from 0 to 1 times 2, you would go into R sign, right? Because it would be, you'd end up being left with 1 over square root of 4 minus x squared. And from there, just the arc sign, or
oh no, it's still a just substitution, because here we have a degree 2 and a degree 1. So in this case, this numerator stands for the du part very, very well in this case. So I mean, yes, of course, that x disappears from when we rewrite this in terms of u, and that just becomes a general power rule problem. However, if since the very beginning we didn't have that x, yes, we would have used the arc sign rule. Okay. All right, the next example, the portion of the curve x equals 2/3 y to the 3/2 between 0 and 3 is rotated about the x-axis. Find the area of the resulting surface. All right. So number one, let's have a look. Let's have a look at the graph. Of course, you can use your graphing calculator to graph this one. Well, no, maybe not, because this is a function of y. So, well, we will later learn how to graph functions of y when we go to parametric mode, but that's going to be at the end of the course. In the meantime, well, I will just give you the graph for this. And so, and it looks something like the radical function, right? And in this case, well, so here is the thing. What do we have? We have, number one, functions of y, but we are rotating about the x-axis. So this is where we're finally getting a little bit of a twist in the plot here. So let's see. Number one, so that's our surface. And, well, it's going to look something like this. All right. It's like a sideways cone, if you will. Parabolic cone, if you will. And, well, from here, well, we have a function of y, so let's use the version for the formula for which we have all y. So let me write down the formula. And, well, in this case, there's going to be a little typo in here. these two should be x's, not y's. All right. So please change that on your paper. And let me write down the formula first. So we start with that. Big S equals 2 pi integral from c to d. And what else? That's r of y square root of 1 plus, in this case we use the letter g prime for functions of y. Okay, so let's see. Now when we analyze this region, okay, the most important and typically the tricky part for when setting this up is to determine the radius of the region. And in this case, well, the rotation is going about the x-axis. That means the distance from the axis of rotation to any point on the graph that we are rotating is vertical. In other words, this is in the form of y units, right? So we will replace this r of y with simply y. So 2 pi integral of y 1 plus g prime squared dx. Okay, so now what do we need? We need the derivative of the given function. So let me do that on the side. So of course this function x equals to 2/3 y to the 3/2. It's the same as saying g of y. G of y equals to 2/3 y to the 3/2. So we take the derivative of this function g prime. This is, well, 3/2 times 2/3. Y to the 3/2 minus 1, isn't that 1/2? And what's going to happen here? Don't you see these 3/2 and the 2/3 are just going to cancel, making this look really simple? Well, they cancel, and y to the 1/2 is simply the square root of y. And see how nice this integral will be compared with the ones that we have done up to this point. So 2 pi from 0 to 3 y square root of the 1 plus the square root of y squared dy. All right, so let's have a look at this integral. All right, okay.